Our ideal op-amp rules are simply number one, no current may flow into or out of the input terminals of an ideal op-amp. And rule number two is that there can be no voltage difference between the input terminals of an ideal op-amp. So rule number one comes about because we are considering an ideal op-amp to have an infinitely large input resistance. So we're effectively seeing an open circuit when we look into the input terminals. No current can flow. That's fairly straightforward. Rule number two, our voltage constraint actually comes about from the fact that we have zero output resistance and an infinitely large open loop gain. So just for the sake of argument here, if we drew the output stage using the practical op-amp model, let's just say we were going to draw this circuit. Plus, here's R1. Here's our input voltage, VCC plus, VCC minus. Here's RF, and here's V out. Using the practical op-amp model, our circuit would look something like this. This is an infinitely large resistance or an open circuit. Here's AVOL times V plus minus V minus, our differential voltage. Here's R out, plus minus V out like so. Here's V plus, here's V minus. Here's R1. Here's RF. Here's VN. So we know this current, that's supposed to be a different color, has to be 0 amps because it sees an infinitely large resistance. R out over here is supposed to be, 0 ohms, not 0 volts, which means V out is exactly equal to AVOL times V plus minus V minus, right? Positive polarity on top. And this V minus like so, which means V out over AVOL will be equal to V plus minus V minus. Well, if AVOL is infinity, any output voltage we see divided by infinity is going to look like 0, which means V plus minus V minus is equal to 0, or V plus is equal to V minus. So this is our voltage constraint relationship, and it occurs because we are assuming an infinitely small output resistance and an infinitely large open loop gain. So just to let you guys know where these rules came from, the application of these rules allows us to analyze any single stage op-amp circuit with effectively 3 simple steps, right? So our first step, so let me, I guess, write this here real quick. Negative feedback op-amp analysis. Step 1 will be to apply rule number 1. And determine V plus, the voltage present at our non-inverting input node. Step 2 will be to apply rule number 2 and perform KCL at the inverting input node. And step 3 is simply solve the KCL equation for V out. So if we can apply these 3 steps, we will be able to analyze pretty much any single stage op-amp circuit that we're going to look at in this particular class. So this is what we should default to if we're ever given anything that we don't recognize after today's lecture, where we cover all of the commonly used circuits. Okay. And we are going to use these 3 steps in order to develop our input-output relationships and all of that kind of good stuff for these circuits. So now let's move along to common negative feedback op-amp topologies. And just for sake of argument, common of negative feedback op-amp topologies. When is our first test in this class? Friday. I agree. How many of you guys have clicked down to where it says exam number 1 on Moodle? Nobody? Okay. Let's do that just real quick. I can find my mouse cursor. Let's do this the other way. Come on, board. B. Circuits 2. If we scroll down to where it says exam 1, you guys probably can't see this yet because I've already uploaded your take-home portion so that I don't forget to do it. Lock is going to open up at probably noon, I think, on that Friday. But this first link doesn't have a lock on it, which means you can look at it now. This is your equation sheet for your exam. Providing it to you. On the front page, it includes a practical op-amp model, open loop op-amp circuit, so your non-inverting and inverting comparators and the relationships for them. And then your positive feedback op-amp circuits that you might be tested on, so your non-inverting Schmitt trigger, your inverting Schmitt trigger, and the relationships that you use to calculate the upper trigger limit and lower trigger limit. The back page is literally what we're covering today. Negative, go away, antivirus. The 6 different types of amplifiers that we are going to cover today. I'm going to expect you guys on your exam using this equation sheet to be able to identify the different types of amplifiers as part of a cascade, which is what we're going to be talking about in class on Wednesday, and then effectively just use these relationships instead of applying the 3-step process in order to figure out what the heck is going on. I wanted to make you guys aware of this equation sheet so that you can look at it beforehand and familiarize yourself with it, but I believe it's pretty straightforward. So, anywho. Common negative feedback op-amp topologies. The first one that we're going to look at is the classic, let's see, this would be an inverting amplifier. I'm not going to draw the power supply voltages or anything on any of these circuits. We are going to assume that our op amps are biased correctly to provide the amplification that we're trying to get. So here is our negative feedback, our inverting input terminal. Here's our non-inverting input terminal. Here is our output terminal for the inverting amplifier. We should have a negative feedback resistor RF, like so. Here's where we take V out. Our inverting input terminal should be directly, well, it should be grounded. We'll talk about that in a moment. We should have some resistance here, R1. And then this is where we're going to apply our input voltage. This is exactly the circuit that we analyzed using the practical op-amp model in Friday's class. If we apply op-amp rule number 1, we will recognize that this current is 0 amps and this current is 0 amps. So our voltage at this node is simply 0 volts. Step 1 is taken care of. Step 2, we apply op-amp rule number 2. V minus is equal to V plus. So this is 0 volts. And now we're going to apply Kirchhoff's current law at the inverting input node. Let's do that in green. So this current plus this current will equal to 0. So that's going to look like 0 volts minus whoever whoever isn't muted, please mute yourself because it's getting weird feedback. 0 volts minus V in over R1 plus 0 volts minus V out over RF will be equal to 0. Solving this, we find that V out is equal to negative RF over R1 times V in, which means our closed loop voltage gain, so AV closed loop, which will be the system output voltage divided by the system input voltage, is simply negative RF over R1. So ways that could be used to potentially trip you up. Let's do these in this purplish color. If I put some load resistance between my output node and ground, does it change my relationships at all? No, not even a little bit, right? So the presence of a load resistor here does nothing with respect to our output voltage. It is going to have some effect on whatever current is flowing out of the output terminal because there's another conduction path, but largely we don't worry about that a whole heck of a lot. Although it definitely, I definitely ask you questions about it in your homeworks. Another place I can put a resistor to mess with you. I'm just going to call this resistor here R plus. It's connected to the non-inverting input node. Will it have any effect whatsoever on our relationships? Absolutely not. Very regularly when we make op-amp circuits, though, we'll put some resistance there. It's to eliminate what's a phenomenon called input offset currents. Effectively, they're very, very small currents that can flow and will cause your output voltage to drift slightly. And so you just use a resistor there to correct it. For our analysis, it does nothing, but in a practical sense, it does have a use. Much like a load resistor, that's something that we're trying to drive using this amplifier circuit, but from the analysis perspective, it really doesn't do anything, so we very often don't include it. So this inverting, or this particular amplifier is called an inverting amplifier because the input signal is applied through this resistor network to the inverting input terminal. Okay. In an inverting amplifier, we can get both gain. So if RF is greater than R1, our output signal is boosted, or it's larger than our input signal, but we can also get attenuation, meaning if RF is less than R1, our output signal is smaller than our input signal. We get both of these, so we get both gain and attenuation at the expense of our output signal will always be 180 degrees out of phase with our input signal. Okay. So we're always changing the sign of whatever our input signal is and then scaling it by some amount given by the resistors. Now let's look at the non-inverting amplifier. It is an incredibly similar circuit. In fact, the only difference is that we are changing where we apply ground and where we apply VN on the input side of our device. So starting with our op-amp by itself, we're going to have negative feedback. We're going to have a resistor R1 between the inverting input terminal and ground now, and we're going to apply VN directly to the non-inverting input terminal. We'll measure V out, same place. So applying op-amp rule number 1, we have 0 amps of current flowing into the input terminals. And so the voltage V plus, or the voltage present at our non-inverting input terminal, is simply Vn. Applying op-amp rule number 2, V minus will be equal to V plus, so this node is Vn as well. Performing Kirchhoff's current law gives us Vn minus 0 volts over R1 plus Vn minus V out over RF is equal to 0. So this looks like Vn times 1 over R1 plus 1 over RF is equal to V out over RF. Multiply both sides through by RF, and we get V out is equal to 1 plus RF over R1 times Vn. And therefore we have a closed loop gain of 1 plus RF over R1. So this is the non-inverting amplifier because our input signal is applied directly at the non-inverting input terminal. Just like we saw with comparators and Schmidt triggers, if the input's on the inverting side, we have some type of inverting amplifier. If the input is on the non-inverting side, we have some type of non-inverting amplifier. This particular amplifier can only boost signals, right? So the quantity 1 plus RF over R1 will always be at least 1, which means we can only make signals either the same as our input or larger. There is a special case of this amplifier where RF is 0, a short circuit, and R1 is infinity, an open circuit. That is called a unity gain buffer. And its whole job is to recreate the input signal at the output while providing effectively an infinitely large input impedance. So effectively, if we have a source connected to our input that isn't capable of driving a large amount of current, so something like a piezoelectric crystal or something like that, that's really good at creating voltages and pretty terrible at making currents that go along with it, we can run that output signal from our piezoresistive crystal, which is some part, or piezoelectric crystal, which is part of some sensor, through an op amp to provide us a good output signal without worrying about the need to drive some load or something like that. So it provides isolation between stages. So that's what unity gain buffers are used for. Makes an exact copy of the input signal, but provides isolation between those stages so that whatever is connected at the load is effectively driven by the power supply as opposed to the thing that's generating the source to begin with. So I don't think there are any biomedical engineers or anything like that in this class, but this is a pretty standard input stage for any bioinstrumentation system that you're going to deal with. Let's see. Anything else I want to talk about with this one? I don't think so. All right. Yeah, so at the non-inverting input terminal for the non-inverting amplifier, we have Vn. For the inverting amplifier at the non-inverting input terminal, we have ground. So the only difference between these two circuits is literally us swapping those voltages, right? We move ground from the inverting pin, or excuse me, the non-inverting pin to the leg of the resistor R1. We move Vn from this leg of resistor R1 over to where ground was. It's literally just swapping those two voltages. And for those of you that had me for circuits 1 when we were doing the lab, I literally designed the circuit in such a way that I could swap the two wires to make life easier instead of having to rebuild the circuit again. Okay. So, all right, so let's look now at the weighted inverting summer. So this circuit is nothing more than a modified version of the inverting amplifier. And we are modifying it so that we can have multiple input signals. So here is our resistor RF. I'm just going to ground my non-inverting input terminal. And then over here, I'm just going to apply multiple resistors. So let's call this R1 and it's associated with some source voltage V1. Let's call this guy R2. It will be associated with some source voltage V2. This guy up top will be R3. It'll be associated with some source voltage V3, and we could keep on going. There isn't a practical limit to the number of inputs that we could apply to this thing, as long as they're applied at this particular terminal. Here is our output signal. The out. And once again, just going through the simple three-step process, we know that we have 0 amps flowing into the input terminals. We can see by simple inspection that the voltage present at our non-inverting input terminal is 0 volts, which means the voltage present at our inverting input terminal must also be 0 volts. If we apply Kirchhoff's current law at our inverting input node, we will get 0 volts minus V3 over 3 plus 0 volts minus V2 over R2 plus 0 volts minus V1 over R1 plus 0 volts minus V out over RF is equal to 0. Rearranging things here, we get V out is equal to RF times, excuse me, negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. So we're not going to really have a voltage gain here because we have 3 inputs, so that's a little bit hard to define. We could define a voltage gain for each individual input, and it's simply negative RF over the resistor associated with that input, because this is nothing more than an inverting amplifier where we're just putting multiple input signals on the inverting side. So the reason why this is called a weighted inverting summer is because each individual input voltage, V1, V2, and V3, gets weighted or scaled by a different amount based on the ratio of these resistors, right? So V1 gets scaled by a factor of negative RF over R1, V2 gets scaled by a factor of negative RF over R2, V3 gets scaled by a factor of negative RF over R3. If R1, R2, and R3 are all the same value, we no longer have a weighted inverting summer, we just have an inverting summer because all of the different input signals are scaled by the same amount. This circuit is how your bathroom scale works if you have a digital one. There are 4 inputs corresponding to 4 load cells at each corner, each of the 4 corners of your scale. They generate a voltage based on the amount of strain that they undergo. So it's usually some sort of nickel strain gauge and a piezo resistive configuration. When you step on it, causes a strain that generates some sort of output voltage at each of the 4 corners. Those output voltage are effectively added together and scaled by some amount that is converted into your weight. This is how the really large weigh stations work. When you go drive across state lines and all that kind of stuff, it's the same basic thing, right? If I were feeling absolutely crazy, I could develop a weighted inverting summer that would take your test grades and give you your output average in the class if I were just feeling real squirrely, because that's the whole point of this thing, is to take a weighted average of different components. Not going to do it because it sells way easier, but this could be done. So this is one way that we can add signals together. Now, technically speaking, you could also have a non-inverting summer. We could apply multiple input signals to the non-inverting side as well, but the math does not work out nearly as prettily as this does. Okay, so generally speaking, if you wanted the output of your inverting summer here to be positive, you would simply run this into a second amplifier stage that would just flip the polarity of the signal. And the math is way easier using 2 op amps than it is using a single op amp. I would argue the increase in cost is, to me, cheaper than the amount of thought that requires into figuring out how to scale everything correctly using the other configuration. All right, Now let's look at the differencing amplifier. So we just added signals together. Now let's take the difference of signals. So the differencing amplifier takes advantage of the fact that the inverting input terminal causes the output signal to change polarities, and the non-inverting input terminal causes the output voltage to maintain its polarity. So if we apply a voltage signal to both of them, we're going to wind up getting some difference in voltages. So we have our feedback resistor. I'm just going to call this R. A resistor here connected between the inverting input terminal and our input signal V1, also R. We're going to have a resistor here, also R, between the non-inverting input terminal and ground. And then we have a fourth resistor, also R, between the inverting input terminal and our input signal V2. Here is where we are going to take our output. So our input signal V1 is applied through our feedback network to the inverting input terminal. Our input signal V2 is applied through this resistor network. It's a simple voltage divider, but if you don't believe me, we can throw math at it and prove it. And then the output voltage, as I said, will simply be a difference, but let's do the math here, right? So this current is 0 amps. This current is 0 amps. So our voltage V plus here is just going to be 1/2 of V2. We can get that by using voltage division. We can get that by saying that there's a voltage drop V2 across 2R in series, giving us a current of V2 over 2R. Multiplying that by R gives us 1/2 times V2. We could also disconnect this network and find the Thevenin equivalent, and it would still give us the same result. So it really doesn't matter how we slice it. Our voltage at this node is going to be exactly 1/2 of whatever V2 is, as long as these two resistors are matched. Applying rule 2, we know that this voltage here at our inverting input terminal is V plus, so that is also 1/2 V2. And now we will apply Kirchhoff's current law. So that's going to be 1/2 of V2 minus V1 over R plus 1/2 of V2 minus V out over R is equal to 0. Since we have a common factor of 1 over R, we can multiply both sides by 1 over R, and conveniently for us, 0 times 1 over R is still just 0. So we can just throw away those denominators. And we're going to move V out to the other side, giving us a relationship of V out is equal to 1/2 V2 plus 1/2 V2, or just V2, minus V1. So we simply have the difference of the input signals going up at our output. If we used different values of resistors, we would wind up scaling our different signals by certain amounts. This is the classic case where they're both scaled by a factor of 1. Another way to analyze this circuit, just for the sake of argument, would be to use superposition. So with V1 on and V2 off, this is an inverting amplifier with a gain of negative R over R or -1. So that's why we get a negative signal on V1. With V2 on and V1 off, we get 1/2 V2 here, which means we have 1/2 V2 here. Or excuse me, 1/2 V2 here and a non-inverting amplifier, which would have a gain of 1 plus R over R, or 1 plus 1 is 2. 2 times 1/2 of V2 gives us positive V2. So anyway. All right. And then for the circuits that some of you may not have seen before, because I don't know if Dr. Schwanbaum, Dr. Reese, or Dr. Kronk or anybody else does the calculus relationships. Yes, Hannah.
So what is the benefit of the summary or the different?
How would you get the difference of two voltages doing whatever voltage you want, as you called it? Like this, the op amp, its purpose is to perform mathematical operations on electrical signals, right? We are doing everything here with the assumption that everything is a DC signal, but that's not really what op amps are actually used for. DC is boring, right? But if we wanted to figure out what the difference between two signals was, so let's say that we had a message signal superimposed on top of a carrier signal in some sort of AM modulation scheme. This is how radio signals work. Well, if we subtract from that combination of signals the carrier signal, we are left with just the message signal. We demodulated it to get the information that was actually transmitted on top of that carrier, right? We're going to find out in here just a moment when we do integrating signals or excuse me, the integrating amplifier and the differentiating amplifier, that not only can we do addition and subtraction with a single op amp, we could also do integration and differentiation. Well, the integration operation and the differentiation operation are the fundamental building blocks of automatic control systems used to control processes and all of that kind of good stuff. They also happen to be the fundamental building blocks of active filters used for passing some portion of the electromagnetic spectrum and rejecting some other portion. So the short answer is these are what are used. These the op amp and these particular configurations are the fundamental building blocks of analog signal processing, right? So most of us are used to digital signal processing because that's what computers and all that kind of good stuff do. If you go down the hall, come out towards the door here, and then hang a left, and you go to the guy whose office is directly below mine. His name is Ron Lewis. Okay, Ron Lewis is actually doing active research on analog computing because there are certain problems that analog computing using these guys does better than digital computers that we are used to. So it's still, even though the op amp as an integrated circuit, it really didn't exist until integrated circuits did in the, I think, late 50s, early 60s. The op amp topology, putting all the transistors together and all that kind of stuff, came out shortly after World War I. Been in use for over 100 years. It's still absolutely integral to how most analog signal processing works. All right, let's do calculus with op amps. So this is going to be the differentiating amplifier. So this is the one that will be used to perform a derivative. And it is nothing more than an inverting amplifier where we're going to replace one of our resistors with either a capacitor or an inductor. I am going to derive things using capacitors. In practice, you will more likely use a capacitor to make an integrating amplifier or a differentiating amplifier than you will an inductor, because the tolerance on capacitors is better than the tolerance on inductors. So effectively, you're going to get closer to what you want using capacitors. But the mathematical relationships, like so theoretical relationships, it really does not matter. And as a matter of fact, I make you derive one of them in one of your homeworks using inductors instead of capacitors. So we have our simple op amp like so. We are going to tie our non-inverting input terminal to ground. For this particular circuit, we are going to have a resistor in our feedback loop. We are going to put our capacitor here. And because we're dealing with a capacitor, I'm going to explicitly state that my input signal needs to be time varying, because this gets wildly boring if we just use DC signals. We don't get anything. So just as a brief refresher here, the current flowing through a capacitor is given by C times the derivative of the capacitor voltage with respect to time. And the voltage drop across the capacitor is 1 over C times the integral from -infinity to some later point in time of IC T prime dt prime, where I'm not using the initial condition relationship here just because that's going to make the math slightly more difficult and I don't want to do it. Okay. So I am going to call, let's see, what color haven't I used? I don't think I've used this one. The polarity of my capacitor voltage will be positive polarity on the left, like so. And my capacitor current will be directed to the right so that it's flowing into the positive polarity terminal of the capacitor. Right. So if we apply ideal op amp rule number 1, we know that no current can flow into either of our input terminals. And we can see that the voltage present at our non-inverting input terminal is 0 volts, which means the voltage present at our non-inverting input terminal must also be 0 volts. Now I'm going to apply Kirchhoff's current law at this node, but I'm going to do it very slightly differently than I've done it before, because I've already defined a current along this path as flowing in. So I'm going to say that this current flowing in is equal to this current flowing out. Okay, still doing the same 3-step process. Here's my current flowing out. So I have, well, we'll do it down here. IC of T will be equal to 0 volts minus V out divided by RF. Okay. Can't really solve this one just yet. So what I'm going to do now is I'm simply going to substitute in this top relationship for IC, so that I will have C dV by dt will be equal to negative V out over RF. And I'm just going to rearrange things here really slightly and say that V out will be equal to negative RF times C times the the derivative of my capacitor voltage. And the last thing that I need to do is figure out how VC and VN relate to each other. So somebody tell me what that relationship is. What is the relationship between Vn of t and the Vc of t in this circuit? They are the same thing. Vn is measured between this terminal and ground. Vc is measured between this terminal and 0 volts, which is effectively ground. So Vn and Vc are the exact same thing. So we see that our output signal is just a scaled version of the derivative of our input signal. Now, when we are implementing a differentiator like this, which I am going to, I don't remember if it's a take-home test question or a design question. So let's find out. Design projects. Project number 1. Boop, boop, boop. Project number 4 down here, should you choose to attempt this, says to design a multi-stage op-amp network which can convert a 1 volt peak-to-peak sinusoidal input voltage into a 1 volt peak-to-peak square wave and a 1 volt peak-to-peak triangular wave. So let's talk our way through this really quick here. If we had a 1 volt peak-to-peak sinusoidal input, how do you think we could get a square wave out of it? A comparator, absolutely right. Then we want to take the output from our comparator and generate a triangular wave. So actually this would wind up using an integrator, not a differentiator, because the integral of a square wave should be a triangular wave. But what we need to think about is the fact that we have energy storage elements, particularly capacitors, that take a certain amount of time to charge and discharge, right? So our frequency of interest, which in this case is 1 kilohertz, is going to be in some way, shape, or form related to the product of R and C, because that's what our time constant is for a RC circuit. Still holds true here, you know, so just be aware of things like that when you are working on these problems, particularly the ones that don't have just strict DC components, right? So just for the sake of argument, this is a DC circuit, this is a DC circuit, this is a DC circuit, this is going to be an AC circuit. And if this is on these design projects, then your take-home design problem that I'm making all of you do is also an AC circuit. It's part of your test. So time constants, things like that that you learned in circuits 1 still very much matter. And if you get to simulating these things and it's not behaving like you expect it to, instead the voltage or whatever is just gradually getting larger and larger and larger, it's because you're not letting your energy storage elements discharge enough between cycles. Can't just throw any resistor and capacitor in there and expect it to work. I know. You have to think about things, the horror of it all. All right, so my screen will switch back. Now we're going to make an integrating circuit by the magic of swapping the R and the C. So literally the exact same circuit, except we are changing the position of our resistor and capacitor. So now we're going to have a capacitor up here. Call it CF just for the sake of argument. Minus plus Vn of t. Let's define our capacitor voltage like so. And our capacitor current like so. We know that this current is 0 amps and this current is 0 amps. We can observe easily that this voltage is 0 volts, which means this voltage is also 0 volts. And now we're going to apply Kirchhoff's current law, much like we did with the differentiator. We're going to say current flowing in is equal to current flowing out. So that's going to give us the relationship Vn minus 0 volts over R will be equal to IC of t. We're going to replace IC of t actually, so now we need to think about some things here just very, very quickly, right? Because we're expecting to have some relationship between Vn and V out for this thing. And right now we have Vn in terms of IC. So how is V out related to VC? Let's start there. Not quite. Exactly right. They're same magnitude, opposite polarity, right? Because V out, the positive polarity terminal is here, the negative polarity terminal is at ground. VC, the positive polarity terminal is at ground. So V out and VC are just equal but opposite, right? So let's write that over here. So this is supposed to be an integrator. So I want to take the integral of both sides. Having a little bit of a brain fart here to remember how the math shakes out. We know that VC of t, let's just look at it. I think we have everything we need right here. So if V out is equal to negative VC, then V out is equal to negative 1 over CF times the integral from negative infinity T of IC of T prime dt prime. If we substitute in our relationship that IC is equal to Vn over R, this comes out to be negative 1 over, keep writing the F first, CF times the integral from negative infinity to T of Vn of T over R, or T prime dt prime. I'm going to pull my R out so that I have negative 1 over R CF times the integral from negative infinity to T of Vn of T prime dt prime. There we go. Now, in practice, this integrator circuit is usually slightly modified from this. The math works out effectively the same, but there would be a resistor in parallel with that capacitor CF. And the purpose of that resistor in parallel with that capacitor means that our initial condition on the system will always be that our capacitor voltage starts at 0 because we're giving it something to discharge to. Okay. We could go through the analysis. It's tedious using things in the time domain. Once you learn how to do analysis of circuits in a frequency domain using the Laplace transform, this is a real something. So this is something that, well, you haven't taken circuits 3 yet. This is something that you will do specifically in circuits 3 when you're talking about filters and all that kind of jazz. So we're going to leave this as is to not spend 20 minutes on math. It's completely and utterly unnecessary if we were just using Laplace transforms. All right, so we have talked about how we do analog signal processing with op-amps. We have covered adding signals, subtracting signals, scaling signals, integrating signals, and differentiating signals. All right, so that is enough out of me for today. Our next class meeting will probably be even shorter than the hour we spent today, where we're just going to be talking about cascading op-amps. All that means is that we're going to connect multiple op-amps together to do things. That's it. So effectively, the output of this op-amp would serve as the input for the next stage, and so forth and so forth. And that's how you can make complex architectures to do fancier things than just what a single op-amp can do. Gabriel. Yes.
Could you build differentiators with complexity?
Yeah, absolutely.
You just like swap.
Yeah, so if you wanted to build, let me scroll up here. So if you wanted to build a differentiator with an inductor, the inductor would go here and the resistor would go here. It's because their current voltage relationships are opposite, so they have to have the opposite position. But yes, and like I said, I believe in your next homework assignment, I make you derive one with an input. Yes, Joseph, I believe. Why would you use? So this particular circuit, we are calling it a differentiator because that's exactly what it's doing based on the input-output relationship. It also happens to be I think this is a low-pass filter from the perspective of steady-state sinusoidal circuits. It is a building block of both communication and control systems networks, just like this guy right here, if I'm remembering correctly, is a high-pass filter, which is also used in automatic control systems and communication systems as well. So these op-amp circuits, anytime you want to do analog signal processing, your phone probably has 20 different analog signal processing circuits on it, most of which are simple op-amp circuits, right? For separating the message signal from carrier signals. So let's think about that real quick. I used that example a little while ago. What frequency do radio stations broadcast at? 80 to 115. Okay. What? No, you're correct, but what? Megahertz. Megahertz. So, what's the range of human hearing? Anybody have any thoughts on that? So the lowest frequency that humans can hear is somewhere in the ballpark of 25 hertz. And the highest frequency that most humans can hear is somewhere in the ballpark of 20 kilohertz. So if the radio stations that we listen to when we drive to campus or whatever, assuming that you guys are old like me and listen to radio stations and not just streaming crap off your phone, but that's an entirely different thing that also uses the exact same principles, because you're using, potentially, if you're connected to satellite radio or using the cell phone network to stream things, you're still doing the same thing. If the audio signals or the radio stations or whatever are broadcasting hundreds of megahertz and we can only hear up to 20 kilohertz, how the hell do we hear radio stations? So that 100 megahertz signal is a carrier signal, and on top of that carrier signal is a message signal. They're superimposed on top of each other. But if you can eliminate the carrier signal by analog signal processing, all you hear is the message signal, which is what you're listening to on the radio. That is a direct application of at least a different signal amplifier, right? For these particular circuits where we can do calculus, that is used to eliminate unwanted portions of the spectrum, right? So while humans can hear from 25 hertz all the way up to 20 kilohertz or more, depending on how good your ears are and how much death metal you listen to as a youth, you might want to eliminate, say, everything below 60 hertz or something like that if you're in a place like this. How many of you can hear the lights humming in this room? Everybody, because it's real loud. That's 60 hertz hum. If you wanted to not pick that up, you would need to use a filter, probably a high pass filter that cuts off everything below about 60 hertz so that it doesn't show up on the signal that you're trying to amplify, which is, I believe, this guy right here, but I might have gotten it backwards because I'm used to using passive filters. Okay. But anyway, so analog signal processing is still literally everywhere. Anytime that we're transmitting a signal over a long distance, we're using some form of analog signal processing to eliminate the carrier frequency and only be able to view the message. Yes. Exactly right. So let's go back up here real quick. So I gave you a gain equation for this one and the one above because there's a simple relationship between the output voltage and the input voltage, right? When we look at the weighted inverting summer, there's a gain applied to each of the individual inputs, but there's not a gain for the system because there are multiple inputs. Similarly here, we can see that V2 experiences a gain of 1, V1 experiences a gain of 1, but overall it doesn't particularly matter because we're looking at a combination of inputs. The reason why we don't really have gains here and let's see, here and here is because we have these calculus-based relationships, right? So instead of saying V out is related to V in by a number, V out is related to V in by a number and also a mathematical operation. So instead, and we don't really do this in the time domain, in the frequency domain, we would relate these two quantities, the input voltage to the output voltage, by what's called the transfer function of the system, where the transfer function of the system is literally the ratio of the output voltage to the input voltage. And it will depend on frequency, which will be true for these if we weren't looking at them as a function of time. So short answer is, yeah, the gain doesn't matter, so don't worry about it.